In this session, we are going to discuss about the method for deriving Debye-Huckel-Onsager equation. So we already discussed about Debye-Huckel-Onsager theory, in which we said that there is formation of ionic atmosphere, and each ion in a particular solution would be surrounded by oppositely charged ions, and these ions will be forming an ionic atmosphere surrounding that particular central ion. And we also mentioned that for strong electrolytes, the conductivity will be reduced when you increase the concentration. That is because of the decrease in mobility of the ions, and the strong electrolytes will be completely dissociated in a particular solution. And we also mentioned that the ionic interaction, so the interaction between various ions in a solution will be following Coulomb's law of electrostatic interactions. So when you derive, now we are going to derive Debye-Huckel-Onsager equation. So you can actually consider this particular process to be containing different steps. In the first, we will be considering how ionic atmosphere is formed, how it is formed, what is the various number of ions, or the electrical density, potential density in that particular ionic sphere. And then we will be considering the electric potential at the center of the volume element dV forming the ionic atmosphere. What is the potential at that particular region around a central atom? And then we will discuss how you can determine the thickness of ionic atmosphere and the various factors that affect the thickness of ionic atmosphere. And various forces the ion experience in a potential field will be discussed. And using that, we will be equating the various forces, and using those we will be deriving the Debye-Huckel theory. And after deriving a few relations, we will be introducing the equivalent conductance term, and after various assumptions like dilution of the medium and the bivalency of ions, etc., we will be arriving at the Debye-Huckel-Onsager equation. So according to Debye-Huckel theory, the main postulate is that every ion is surrounded by an ionic atmosphere of oppositely charged. So whenever you are considering a central ion, it will be surrounded by an oppositely charged ion. So you cannot say that in a particular solution it is only that kind of only the oppositely charged ion is surrounded by the surrounding the metal ion. So you cannot say, if you're considering a positive ion as a central ion, you cannot say only negative ions are present around this central ion, because due to thermal motion there can be positive as well as negative ions. But the time average, when you consider the time average and the number of ions present around that particular positive ion, you can see that a majority of the ions that are present around this positive ion would be negative charged ions. So surrounding a particular ion, there can be ions of both same charge as well as opposite charge. But when you consider time average, the number of oppositely charged ions will be more due to the inter-ionic interaction or attractive force between the oppositely charged ions. So this is the basic assumption or basic postulate of the Debye-Huckel theory, and we will be starting the derivation of this particular equation, where you can connect the equivalent conductance to the concentration of a particular electrolyte, can be started from this point, a point where you consider the central ion to be surrounded by negatively charged or the oppositely charged ions. So consider a positive ion situated at a point A. Here you have a positive ion that is situated at a point A, and consider a small volume dV that is at a distance r from the positive ion. So we are considering this kind of thing, that is, you have a positive ion and you are considering a small volume element dV that is situated at a distance r, and this r is very much less than the diameter of ion. It is 100 times less than the diameter of ion. And the thermal moment of ions, there will be sometimes an excess of positive ions and sometimes an excess of negative ions in the volume element dV. So as we mentioned earlier, here can be both positive as well as negative ions due to the thermal motion of the ions. But on time average, because of electrostatic attraction by the positive ion at A, there will be a negative charge density. There will be an increased negative charge density in the volume element dV. So here, since this ion is positively charged due to the electrostatic interaction, an increased number of negative charges will be present here. The net magnitude of charge of the ionic atmosphere of every ion is equal in magnitude but opposite in sign to that of central ion. So if this is having +1 charge, the net charge of the ionic atmosphere will be -1. So the net magnitude of charge of the ionic atmosphere is equal in magnitude but opposite in sign to that of central ion. So these are the basic things that we consider when you begin the particular Debye-Huckel theory, or we first try to derive the relation between the equivalent conductance and the concentration. So how ionic atmosphere is forming, what is the nature of ionic atmosphere, etc. The charge density of ionic atmosphere will be greater in the immediate vicinity of the central ion and will decrease with increasing distance from central ion. This is obvious because it is following Coulombic law. So at immediate vicinity of the positive ion, there will be more charge density for the ionic atmosphere. As you move further, as you increase the distance from that positive ion or the central ion, the charge density will be decreasing. And let the time average of the electric potential in the center of the volume element dV is psi. So this is the electrical potential at the center of volume element V. Psi is the electric potential. The work done in bringing a positive ion carrying a charge plus Z plus epsilon to that point is Z plus epsilon psi. So what we are considering now is that we are trying to bring charged ions, so other ions, to that particular volume element. So this volume element constitutes a part of this particular ionic atmosphere, and we are trying to bring positive as well as negative ions into that particular volume element. And the work that has to be done for bringing this ion to the volume element dV is, in the case of positive ions, it will be Z plus epsilon V. In the case of negative ions, it will be Z minus epsilon V. So Z plus and Z minus are the valencies of the ions, and epsilon is the electronic charge. In most of the cases, you may be familiar with the electronic charge in coulombs, that will be represented in coulombs, that is 1.6 into 10 raised to minus 19 coulombs or something. But usually in our electrochemical theories, we will be using electrostatic unit. That will be something different from that Coulombic unit. So if Boltzmann law of distribution of the particles in a field of varying potential is applicable to the ions, the time average number of negative and positive ions present in the volume element dV can be given as dN plus is equal to n plus into e raised to minus z epsilon psi divided by kt dV, and for negative ion d minus is equal to n minus e raised to minus z minus epsilon psi k divided by kt dV. So this is the average number of negative and positive ions that are present at the volume element dV. So we are now going to calculate the net charge density. So net charge density means you have to find the total charge per volume. So that is given by rho. Rho is equal to the unit charge multiplied by total charge, that is Z plus dN plus minus Z minus dN minus. So here you have positive charge as well as negative charge, and positive and negative can cancel each other. So we are considering Z plus dN plus minus Z minus dN minus divided by dV, that is a volume element, and this can be written like this by substituting the value of dN plus and dN minus. So you get the equation 3 like this. You have epsilon n plus Z plus e raised to minus Z plus epsilon psi divided by kt minus n minus z minus e raised to z minus epsilon psi divided by kt. So this can be rewritten like this, where if we are considering an electrolyte which is univalent electrolyte, then Z plus and Z minus would be equal to 1, and N plus and N minus can be equated to N, that is total number of particles will be the same, and the number of positive and negative ions would be the same for univalent electrolytes. So rho will be equal to N epsilon multiplied by e raised to minus epsilon psi divided by kt minus e raised to epsilon psi divided by kt, and this particular value, that is epsilon psi divided by kt, will be very much less than 1. So after expanding the exponential terms and neglecting the higher terms, you can get a relation rho is equal to minus epsilon square psi divided by kt multiplied by 2n. So suppose the Z plus and Z minus is not unity, you can the Z epsilon psi divided by kt is very much less than 1, you can get a relation rho is equal to minus epsilon square psi divided by kt into sigma I ni zi square. So here Ni is the number of ions present per unit volume, Zi is the valency of the ions of the ith kind. So now we are going to find what is psi. What is the value of psi? Psi is actually the electrical potential at the center of volume element dV, and using Poisson equation you can solve psi. This equation actually is actually used in studying the interaction in electrostatics, and we are trying to apply that in the case of ions also. And this relationship between the electrical charge density rho and the electrical potential is given by Poisson equation, and in rectangular coordinates you can get a relation like this, where dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square is equal to minus 4 pi rho divided by d. Here the d is the dielectric constant of the medium, rho is the electrical charge density, x, y, z are the coordinates, and d is the dielectric constant of the medium. Since ionic atmosphere is spherically symmetrical and independent of theta, we can actually write this equation in polar coordinates also. And when you write in polar coordinates, you will be having the various coordinates such as r, theta, and phi. The theta and phi would be describing the angle used for showing the orientation of that particular point. So in spherical coordinates, you will be having the relation 1 by r square into dou by dou r multiplied by r square dou psi by dou r, that is equal to minus 4 pi rho by d. We can substitute the value of rho in this particular equation. We have already found the value for the electrical charge density, and we can substitute that value in this particular equation to obtain 1 by r square dou by dou r square dou psi by dou r is equal to 4 pi epsilon square divided by dkt psi sigma ni n zi square. So we can consider all these terms other than psi to be a value equal to kappa square. We are assigning that these terms to be kappa square, and kappa is equal to root of 4 pi epsilon square divided by dkt sigma ni zi square. So you have to remember this is an important term that will be discussed further in this particular session. So after solving the differential equation, you will be getting a solution like this: psi is equal to a e raised to minus kappa t divided by r, and added with a dash e raised to kappa r divided by r. So A e raised to minus kappa r by r and A dash e raised to kappa r divided by r. So we know that when r tends to infinity, psi will be tending to infinity. But if you look at this particular term, even when r tends to infinity, this particular term will not be approaching 0 unless A dash is having value equal to 0. So if A dash is having value equal to 0, this particular term will be 0, and when r tends to infinity, psi will be becoming 0. So unless this term is 0, we cannot say this condition would be satisfied. So we are assuming for getting the correct observation, we are considering A dash will be equal to 0, and thus the equation will be becoming psi is equal to A e raised to minus kappa r divided by r. And for very dilute solution, we can actually think that sigma ni zi square is 0, hence the kappa value will be 0. So we know that in kappa we have a relation like this. Kappa is equal to 4 pi epsilon square divided by dkt sigma ni zi square. So if this term is very small, this term is 0, kappa will be 0, and you can write this equation A by r is equal to zi epsilon divided by dr, or A will be equal to zi epsilon divided by d. So you can substitute the value in the equation, and you will be obtaining psi is equal to zi epsilon divided by d into e raised to minus kappa r divided by r. This equation can also be written like this: zi epsilon divided by dr minus zi epsilon divided by dr multiplied by 1 minus e raised to minus kappa t. And this particular equation, the 1 minus e raised to minus kappa r, can be ignored because it is a very small term when the solution is very dilute. So we can write this equation as psi is equal to zi epsilon divided by dr minus zi epsilon kappa divided by d. So the first term will be corresponding to the potential at a distance r due to the given point ion, and the second term will be the potential arising from the ionic atmosphere, because the term kappa is involved here. So this is the potential, electric potential at a particular point, and this term involves two different terms, and one will be corresponding to the potential at a distance r due to the given point ion, and the other one will be the potential arising from the ionic atmosphere. So this particular term corresponds to the ionic atmosphere, and it is related to the ionic atmosphere. So psi I, the potential due to the ionic atmosphere, can be given as minus zi epsilon kappa divided by d, and this expression is independent of r. When r is equal to 0, the potential on the ion itself due to its ionic atmosphere is given by this particular equation. When the distance between the ionic atmosphere and the central ion is 0, you can have this particular relation. So coming to the thickness of ionic atmosphere, the thickness of ionic atmosphere will depend on the number of ions of each kind present in unit volume and on the valency. If C is the concentration of ions of the ith kind, Ci is the concentration of the ion of the ith kind expressed in moles per liter, then Ni is equal to Ci multiplied by N by 1000. N is the Avogadro number. So we can substitute this value in the corresponding equation, and we can obtain that 1 by kappa is equal to dt by sigma Ci zi square multiplied by 1000 k divided by 4 pi epsilon square n, the whole raised to 1 by 2. So this is the value of 1 by kappa. 1 by kappa is actually the thickness of ionic atmosphere. So we already found what is kappa, and now we are substituting the values corresponding to n and other terms in that particular equation to obtain that particular value for 1 by kappa. And this shows that thickness of ionic atmosphere decreases with increase in concentration and valency of ion. So when you have an ionic atmosphere, the thickness will be depending on the concentration as well as the valency of ion, and as the thickness and valency increases, the ionic atmosphere thickness would be decreasing. The thickness of ionic atmosphere increases with increase in dielectric constant of the medium and temperature. The thickness of ionic atmosphere is to be the order of 10 raised to minus 8 centimeter. So we have found for various ionic atmosphere it will be in the range of 10 raised to minus 8 centimeters to minus 1 at 25 degrees Celsius. So for water, we calculated the ionic atmosphere at 25 degrees Celsius to be at 298 Kelvin to be 1 by kappa is equal to 4.31 into 10 raised to minus 8 divided by sigma Ci Zi square the whole raised to 1 by 2 centimeter. So in water, this would be the particular value. If you are able to find the, if you are taking some electrolytes and then you can find the exact value for the ionic atmosphere that can be occurring in that particular solution. Now we have discussed how ionic atmosphere is forming and what is the thickness of ionic atmosphere and all. So according to the Debye-Huckel theory, we already said that when the particular electrolytic solution is influenced by a particular potential, the ions will be moving. Prior to the immersion of the electrodes and application of the potential, each ions will be surrounded by a ionic atmosphere. And we already said in our previous classes that when you apply a potential, the ions will be trying to move towards the corresponding electrodes, and there will be some forces that prevent the motion of the ions. And if you're considering a particular ion in a solution, you can say there will be some forces that is acting on the ion. So please remember the last classes, and you may be remembering that there will be a relaxation force that arising due to relaxation effect or asymmetric effect of the ionic atmosphere on the ion, and there will be electrophoretic force that is arising due to the movement of the solvent that was associated with the ionic atmosphere, and there will be frictional force of the media. These three forces will be reducing the motion of the particular ion. So they will be reducing the speed of that particular ion in a electrolytic solution. There will be one force that would be that will make the ions move. That only force is the force of the applied field, force due to the applied field. So when you apply a potential, the ions will be moving. Only then the ions will be trying to move towards the electrodes. So this is the driving force for the motion of the ions. All the three other forces will be blocking or preventing the motion of the ions. So now we are moving on to the first force, that is the relaxation force. So if a particular kind of ion moves to the right, that the ion will constantly have to build up its ionic atmosphere to the right, while the charge density to the left gradually decays. So in the case of relaxation effect, we already said that ion will be present in a symmetric ionic atmosphere. When the potential is applied, this particular ion will be trying to move towards a particular direction. Suppose it is moving to right, the symmetry of the ionic atmosphere will be lost, and at some point the ion will be moving beyond the ionic atmosphere, and so the ionic atmosphere in which it was previously occupied will have to be decaying, and a new ionic atmosphere has to be formed. So the rate at which the ionic atmosphere to the right forms and that to the left dies away is expressed in terms of quantity called time of relaxation of ionic atmosphere, that is represented as theta. So the time required for breakage and making of this ionic atmosphere, old ionic atmosphere will be broken down and new ionic atmosphere will be formed. The time is termed as time of relaxation. And usually you cannot say this is an exponential decay, and you cannot say it will be in this particular value, but it will be actually, if you think like that, it should be an infinite, the time required should be an infinite time. But actually it was found that after removal of the central ion, the surrounding atmosphere falls virtually to zero at the time 4q theta. Within this particular time, it was found that the ionic atmospheres will be falling to virtual zero value, and this q is given as z plus z minus divided by z plus plus z minus multiplied by lambda plus lambda minus divided by z plus lambda minus plus z minus lambda plus. Here z is the valency, lambda is the ionic conductance. And for binary electrodes, electrolytes, you can have the q value as 0.5. And when an ion of valency Z is moving with a steady velocity through a solution under the influence of an electrical force, the electric force acting on the ion is epsilon ZV. So now we are moving on to the next force, that is the driving force on that particular ion. So when you are applying an electric potential V, that particular ion will be having a driving force epsilon ZV. This is the electrical force acting on the ion. So this would be pulling the ion towards the electrodes. This will be augmenting the mobility, or this would be imparting the mobility for that particular ion. This force is balanced by the force due to resistance represented by Ku. So in the first concept, what we are doing is that the ions would be moving towards an electrode due to a particular driving force that is provided by the potential applied across the electrodes, and any other force that is blocking or preventing the motion is termed as the resistance. And here it is represented as Ku. Ku is the resultant coefficient of frictional force, and U is the steady velocity of ion. Therefore, epsilon ZV is equal to Ku. So at equilibrium condition, or when ion is not moving, you can say epsilon ZV will be equal to Ku, and K is equal to epsilon ZV divided by U. And if the potential gradient is 1 volt per centimeter, you can have V is equal to 1 by 300 electrostatic units, and the velocity U will be equal to lambda by F. There is a relation, U is equal to lambda by F, and K will be equal to epsilon ZF divided by 300 lambda. You are just substituting the value of U as well as the value for V, and if we know the value of F is equal to 96,500, and epsilon to be equal to 4.8 into 10 raised to minus 10 electrostatic units. So the value of K is equal to epsilon ZF divided by 300 lambda, that is equal to 15.4 into 10 raised to minus 8 Z by lambda. So this is an important relation. So we found that there is a relaxation force, and then we found that when you apply the potential, there will be corresponding force epsilon ZV, which will be dragging the ions towards the electrode, and there will be a resistance for that particular ion, which will be given like Ku, and the value of Ku, we substituted the value for V, volt as 1 by 300 electrostatic units, U as lambda by F, and we substituted the various values of F, epsilon, etc. Ultimately, we got K is equal to 15.4 into 10 raised to minus 8 Z by lambda. The Debye and Falkenhagen showed that the relaxation time is related to the frictional coefficients K plus and K minus of the two ions, constituting a binary electrolyte by expression theta is equal to 2K plus K minus divided by K plus K minus multiplied by 1 divided by KT kappa square. So we have this expression, and what we are going to do is that so now we are going to connect this particular potential and the relaxation time, and instead of k we are going to substitute 15.4 into 10 raised to minus 8 set by lambda, and the theta value we'll be getting is 30.8 into 10 raised to minus 8 set by lambda multiplied by 1 by kt kappa square. So 1 by kappa for the aqueous solution is found to be 4.31 into 10 raised to minus 8 divided by sigma ci zi square the whole raised to 1 by 2. So substituting this value we can have theta will be equal to 71.3 into 10 raised to minus 10 divided by c set lambda. So c is the concentration of the solution in moles per liter. So this is the ultimate relation that we have now. Another force that is acting on the ion is electrophoretic force, the tendency of the applied potential to move the ionic atmosphere with its associated solvent molecules in a direction opposite to that in which the central ion, which is with its solvent molecules, is moving. So first, in the relaxation time we mentioned about the movement of central ion. Here we are mentioning the movement of the ionic atmosphere and the solvent molecules associated. An additional retarding influence equivalent to an increase in the viscous resistance of a solvent is exerted on the moving ion. This is known as electrophoretic effect. The electrophoretic force can be given as epsilon Zi kappa divided by 6 pi eta ki v. So here you have kappa, eta and k, and the term corresponding to the voltage that we applied. Here epsilon is the unit charge, Zi is the valency, kappa is the reciprocal of thickness of ionic atmosphere, eta is the viscosity of the medium, Ki the coefficient of frictional resistance of the solvent opposing the motion of the ion of ith kind, and V is the applied potential gradient. So same relation was derived by Onsager in an alternative manner, and Onsager actually introduced the concept of Brownian motion of ions in the particular solution. So that was much more valuable and much more acceptable concept. So now moving on to Debye-Huckel-Onsager equation. In the first derivation of relaxation force, we did not account for the natural Brownian movement of the ions. This was considered by Onsager, and he deduced the equation relaxation force equal to epsilon cube Zi kappa divided by 6 dkt omega v. Here omega will be equal to Z plus Z minus 2q divided by 1 plus q raised to 1 by 2, and the value of q is equal to Z plus Z minus divided by Z plus Z minus multiplied by lambda plus lambda minus divided by Z plus lambda minus plus Z minus lambda plus. So this is a modified equation for the relaxation force that was proposed by Debye-Huckel and proposed by Onsager. And now what we are going to say is that we know which are the opposing forces and which are the moving forces that stimulate the movement of ions in a particular solution under a particular potential field. So when ion is moving through a solution with steady velocity ui, the driving force due to applied potential field is epsilon Zi v. So this is the only force that tells the ions to move or push the ions to move toward a particular electrode. All other forces would be retarding the motion of the particular ion. So this is opposed by frictional force of the solvent, that is given as Ki ui, with electrophoretic and relaxation forces. So we can write at equilibrium epsilon Zi v is equal to Ki ui, that is a frictional force, plus epsilon Zi kappa divided by 6 pi eta into Ki v plus epsilon cube Zi kappa divided by 6 dkt multiplied by omega v. This is the relaxation force. So here you are equating the potential, the force due to the applied field to the frictional force, which is retarding the motion of the ion, the electrophoretic force, which is also retarding the movement of the ion, and the relaxation force which is also retarding the movement of ion. So now we are going to divide that whole equation by kV. You will be getting U by V is equal to, and rearranging you will be getting Ui by V is equal to epsilon Zi divided by Ki minus epsilon Zi kappa divided by 6 pi eta minus epsilon cube Zi kappa divided by 6 dkt multiplied by omega by Ki. If the field strength or the potential gradient is taken as 1 volt per centimeter, B is 1 by 300. In that case, we can write Ui is equal to epsilon Zi divided by 300 Ki minus epsilon kappa divided by 300 multiplied by Zi divided by 6 pi eta plus epsilon square Zi divided by 6 dkt into omega divided by Ki. At infinite dilution, Ui will be equal to epsilon Zi divided by 300 Ki. It's because at infinite dilution kappa will be 0. So this whole term will be becoming 0. Ui will be equal to epsilon Zi divided by 300 kt. Since f u0 is equal to lambda I0, that is at infinite dilution, you have this relation. You can put the value here and you will be getting epsilon Zi divided by 300 k is equal to lambda 0 I divided by f. We also have ui is equal to lambda I divided by alpha f. So alpha is the degree of dissociation. So you can substitute these particular functions here. You can substitute instead of f, you can have alpha f in this particular equation, and you can substitute the value here to get lambda I divided by alpha f is equal to lambda I divided by f minus epsilon k divided by 300 into Zi divided by 6 pi eta plus epsilon divided by 6 dkt multiplied by epsilon Zi divided by k into omega. So what we are doing is that instead of we have a term that is corresponding to the conductance, equivalent conductance, and you have the relation in which you are substituting the equivalent conductance as well as the conductance at infinite dilution. And the second assumption is that the electrolyte will be completely dissociated. Therefore, alpha is assumed to be unity, and this is true for all the strong electrolytes at quite appreciable concentrations, and we can have the relation lambda I is equal to lambda I0 minus epsilon k and kappa divided by 300 multiplied by Zi f divided by 6 pi eta plus 300 epsilon divided by 6 dkt lambda 0 I omega. Since ui0 is equal to epsilon Zi divided by 300 k, epsilon Zi divided by k is equal to 300 ui. But ui0 is equal to alpha lambda I0 divided by f. And we are going to introduce the term kappa in this particular equation, and we are going to substitute the values of epsilon, k and n. We will be having the relation lambda I is equal to lambda 0 I minus 29.5 Zi divided by dt raised to 1 by 2 eta plus 9.9 into 10 raised to 5 divided by dt raised to 3 by 2 lambda I0 omega, the whole multiplied by root of c plus z plus square plus c minus z minus square. The quantities c plus and c minus are the concentration of the ions in mole per liter. They can be replaced by corresponding concentration c in equivalents per liter. And c is same for both ions. If the c is same for both ions, you can write lambda I is equal to lambda 0 I minus 29.5 Zi divided by dt raised to 1 by 2 eta plus 9.90 into 10 raised to 5 divided by dt raised to 3 by 2 lambda 0 I omega multiplied by root of c into z plus plus z minus. The equivalent conductance of an electrolyte is equal to the sum of conductance of the constituent ions. So we can write lambda is equal to lambda 0 minus 29.15 multiplied by Z plus Z minus divided by dt raised to 1 by 2 eta plus 9.9 into 10 raised to 5 dt raised to 3 by 2 lambda 0 omega multiplied by root of C into Z plus Z minus. For univalent electrolyte, Z plus and Z minus are unity. So this particular omega term will be 2 minus root 2, and we will be having the relation lambda is equal to lambda 0 minus 82.4 divided by dt raised to 1 by 2 eta plus 8.20 into 10 raised to 5 divided by dt raised to 3 by 2 lambda 0 into root C. So this equation, the equation 33, this one, 34, 35 and 36 are termed as Debye-Huckel-Onsager equations. And in this equation, you can see the first term will be corresponding to the electrophoretic force. You have the viscosity factor here. And the second term will be corresponding to the relaxation force that is experienced by the particular ion. So here you have the equivalent conductance. Equivalent conductance has infinite dilution as well as the concentration related to each other. The relationship based on the assumption that dissociation of electrolyte is complete. So there is one assumption. The falling of the equivalent conductance at appreciable concentration is due to the decrease in ionic velocity resulting from interionic forces. The decrease of conductance due to these forces is represented by the quantities in the brackets. That is the first and second terms. And the first term in the bracket gives the effect due to electrophoretic force, and the second term represents the influence of relaxation force. For a given solvent at a definite temperature, the magnitude of interionic forces increases with increasing valency of the ions and with increasing concentration of the electrolyte. As long as the dissociation is complete, the concentration is equal to the stoichiometric concentration. But when the cases of incomplete dissociation is there, we have to incorporate the degree of dissociation also in that particular equation. So this is all about this is about how we can derive the Debye-Huckel-Onsager equation. So just to mention one more thing, that is, we have derived a long equation, but when you are trying to study, we can cut short this particular derivation. You have to just mention this part, how you are coming at this formation of the ionic atmosphere. You just can mention how ionic atmosphere is formed, what is the scenario, etc. And then you can straight away mention the corresponding potential at the particular center of the volume element. What is the potential at the center of the volume element? How can it be represented? You can have this relation, and you can give the expanded version of K also. K is actually 4 pi epsilon square divided by dkt sigma ni zi square the whole raised to 1 by 2. So you can first describe how ionic atmosphere is formed, then you can describe the potential at the center of dV, that is the volume element, and you can just give the description of this kappa, that is a value, and you can just mention this 1 by kappa is the ionic atmosphere, and the relation is like this. Or the relation, you can give this relation also, because we are using this relation later in the derivation. And then you can mention various forces that is acting on an ion: relaxation force, electrophoretic force, frictional force, force due to applied field, etc. And straight away you can go to the various equations like this. Here the Q is equal to this. What is relaxation time? What is Q? And what is the force acting on the ion when you are applying a potential gradient? And various equations like this which are useful for describing. So the first part of the derivation can be cut short to a very large extent, because you can just give the relation of psi as well as the thickness of the ionic atmosphere. Later on you can explain these equations according to your wish. But however, the assumptions and the important relation should not be omitted when you are describing this particular derivation. The assumptions are you're using infinite dilution, and the second thing is electrolyte is completely dissociated. And also, some of the cases you will be mainly focusing on univalent electrolyte, etc. So all these will be reflected on the deviations from Debye-Huckel-Onsager equation. When you discuss the Debye-Huckel-Onsager equation or deviation from Debye-Huckel-Onsager equation, you can see all these assumptions will be causing that particular deviation. Assumptions will be minimizing the effectiveness of Debye-Huckel-Onsager theory in many cases. So that's all. Thank you.